We're going to start off with a very brief recap of the Hertzsprung-Russell diagram.
So as illustration, here is the HR diagram for the nearest 16,000 stars. Here we've got absolute magnitude versus the color of the star, and you can see that most stars lie along what is known as the main sequence, which is a simple relationship between temperature and luminosity that goes from high temperature, high luminosity down to low temperature, low luminosity. 90% of stars are on the main sequence, so we can infer that stars spend roughly 90% of their lives there. We know that stars spend most of their lives converting hydrogen to helium, so it's reasonable to connect that with the main sequence. The main sequence is where stars are burning hydrogen to helium in fusion reactions. Here's a schematic of an HR diagram which shows a number of interesting features. I want to remind you of a couple of things. Firstly, the axes. We can convert absolute magnitude into luminosity, as we've seen, and color into temperature. It is customary to plot luminosity in units of solar luminosity. So a luminosity of 100 means that the star has 100 times the luminosity of the sun. Luminosity increases as you go up the vertical axis, which is a standard. Temperature is usually plotted the other way round, however. On the horizontal axis, temperature is plotted so that it increases to the left. This is because as temperature increases, the color index decreases. And when the HR diagram was invented, it was color that was plotted. And we want to keep the overall shape of the HR diagram the same. Here's the main sequence again, and we've seen that that stars lower down on the main sequence, the cooler, redder stars, also have lower masses. The bigger, bluer stars, more luminous stars, tend to have bigger masses. The other parts of the HR diagram, the so-called giants and supergiants and white dwarfs, these are regions we will explore in the next couple of weeks. Now, I'm going to show you yet another schematic of the HR diagram, one which illustrates something simple we can do to understand the size of stars. We know that the luminosity of a star is related to its surface temperature and radius via this formula that comes from black body radiation. If you fix the radius in this equation, then you have luminosity as a function of temperature. So if you fix radius at a certain value, you can plot L versus T from this equation directly on the HR diagram. And these are the dashed lines that you see here. So for example, this dashed line here that passes through the sun's location, that is the line that you get when you plot this equation setting R equal to 1. Note that although luminosity is proportional to temperature to the fourth power, if we plot both luminosity and temperature on a logarithmic plot, this function becomes a straight line. This week I'm going to ask you to plot lines of constant radius on your HR diagrams. With these lines, any star that we plot on this HR diagram, we immediately can estimate quickly its radius, which is a useful thing to be able to do. So you can see immediately, for example, that the higher radius stars tend to be redder but more luminous.